What if you could predict exactly how a curve bends and changes? The second derivative lets you do just that. This powerful mathematical tool reveals the secrets of how functions curve, bend, and change direction. In the next few minutes, I'll show you exactly what this notation means, how to calculate it step by step, and why it's one of the most useful concepts in calculus. By the end of this video, you'll understand not just how to find the second derivative, but why it matters and how it applies to everything from physics to economics. The second derivative is a fundamental concept in calculus that builds directly on what you already know about first derivatives. Simply put, the second derivative is the rate of change of the rate of change of a function. To understand the second derivative, we start with our original function f of x. When we differentiate this function once, we get the first derivative f prime of x, which tells us the rate of change or slope at any point. When we differentiate the first derivative again, we get the second derivative f double prime of x. This tells us how the rate of change itself is changing. In other words, how the slope of our function is changing. The most intuitive real-world example of the second derivative is acceleration. If we have a car moving along a road, its position is a function of time. The first derivative of position gives us velocity, how fast the car is moving. The second derivative of position gives us acceleration, how quickly the velocity is changing. When you press the gas pedal and feel pushed back into your seat, you're experiencing the second derivative in action. The second derivative can be written using several different notations. The most common is prime notation, where we write f double prime of x. We can also use Leibniz notation, writing d² f over dx². This notation emphasizes that we're differentiating twice with respect to x. When we have y equals f of x, we can also write the second derivative as d²y over dx². All three notations mean exactly the same thing, the second derivative of the function. Remember, the second derivative is fundamentally about understanding how the rate of change itself is changing. It tells us whether a function's slope is increasing, decreasing, or staying constant, which gives us powerful insights into the behavior of functions. Now that we understand what the second derivative represents, the next crucial question is, how do we actually calculate it? The process is surprisingly straightforward and follows a clear three-step pattern. The second derivative calculation follows three simple steps. First, we start with our original function. Second, we find the first derivative. Third, we differentiate once more to get the second derivative. Step 1 is simple. We start with our original function. This could be any function, polynomial, exponential, trigonometric, or more complex. For our demonstration, we'll use this polynomial function. Step 2, we differentiate our original function to find the first derivative. Using the power rule and basic differentiation techniques, we get f prime of x equals 3x² plus 4x minus 5. Step 3, we differentiate the first derivative to get our second derivative. Taking the derivative of 3x² plus 4x minus 5, we get f double prime of x equals 6x plus 4. That's it. We've successfully calculated the second derivative. To summarize, calculating the second derivative is a straightforward two-step differentiation process. We start with our function, find its first derivative, then differentiate once more. The key insight is that the second derivative is simply the derivative of the derivative. It's that simple. Now that we know how to calculate the second derivative, what does it actually tell us about the shape of our function? The second derivative reveals something called concavity, the way a curve bends. The geometric interpretation of the second derivative is all about concavity, how the curve bends and curves in space. There's a direct relationship between the sign of the second derivative and the concavity of the function. This relationship helps us understand the shape of curves. Step 1. When the second derivative is positive, meaning f double prime of x is greater than 0, the function is concave up. A concave up function curves upward like a smile. The curve opens upward, and any tangent line lies below the curve. Notice how the curve bends upward everywhere. The arrows show the direction of curvature, always pointing up when the second derivative is positive, Now let's see what happens when the second derivative is negative. Step 2. When the second derivative is negative, meaning f double prime of x is less than 0, the function is concave down. A concave down function curves downward, like a frown. The curve opens downward, and any tangent line lies above the curve. The arrows now point downward, showing how the curve bends downward everywhere when the second derivative is negative. But what happens when the second derivative equals 0? This is where things get interesting. Step 3. When the second derivative equals 0, we have a potential inflection point, a place where the concavity changes. Here's a cubic function that changes from concave down to concave up. The inflection point is where this change occurs, right where the second derivative equals 0. Notice how the left side is concave down, shown in red, while the right side is concave up, shown in blue. The inflection point is exactly where this transition happens. To summarize, positive second derivative means concave up like a smile, negative second derivative means concave down like a frown, and 0 second derivative indicates a potential inflection point where concavity changes. This geometric interpretation helps us visualize what the second derivative is telling us about the shape of our function. Now we'll work through our first example with a polynomial function. We have f of x equals x cubed minus 6x squared plus 9x plus 1. Our goal is to find both the first and second derivatives, then locate any inflection points. Step 1, we find the first derivative using the power rule. The derivative of x cubed is 3x squared. The derivative of negative 6x squared is negative 12x. The derivative of 9x is 9, and the derivative of the constant 1 is 0. Step 2. Now we differentiate the first derivative to get the second derivative. The derivative of 3x squared is 6x. The derivative of negative 12x is negative 12, and the derivative of the constant 9 is 0. Step 3. To find inflection points, we set the second derivative equal to 0. This gives us the equation 6x minus 12 equals 0. Step 4. We solve this equation by adding 12 to both sides, giving us 6x equals 12. Then we divide both sides by 6 to get x equals 2. This means our function has an inflection point at x equals 2. Perfect. We've successfully found that the first derivative is 3x squared minus 12x plus 9, the second derivative is 6x minus 12, and the inflection point occurs at x equals 2. At this point, the concavity of the function changes. Now let's work through our second example using the exponential function f of x equals e to the x. This function has a very special property that makes it unique in calculus. Step 1, we need to find the first derivative. The derivative of e to the x is simply e to the x. This is one of the most important derivatives to remember. The exponential function is its own derivative. Step 2, now we find the second derivative by taking the derivative of our first derivative. Since the first derivative is e to the x and the derivative of e to the x is e to the x, our second derivative is also e to the x. This gives us a remarkable result. All three functions, the original function, first derivative, and second derivative, are exactly the same, e to the x. Here we can see the amazing property of the exponential function. The original function, first derivative, and second derivative are all identical. This makes e to the x incredibly special in mathematics. Now for the concavity analysis. Since our second derivative f double prime of x equals e to the x, and e to the x is always positive for any real number x, this means our second derivative is always positive. When the second derivative is always positive, this tells us that the function is always concave up. The exponential function curves upward everywhere, like a smile that never stops smiling. Here's the graph of f of x equals e to the x. Notice how the curve is always bending upward, demonstrating the concave up nature throughout its entire domain. This upward curvature is a direct result of having a positive second derivative everywhere. To summarize this example, the exponential function e to the x has the unique property that it equals all of its own derivatives. Since e to the x is always positive, the second derivative is always positive, making the function always concave up. Now we'll see how the second derivative becomes incredibly powerful in physics, specifically for analyzing motion. The second derivative isn't just an abstract mathematical concept, it represents something we experience every day: acceleration. In physics, if we have a position function s of t that describes where an object is at any time t, then the first derivative gives us velocity, how fast the position is changing. The second derivative gives us acceleration, how fast the velocity is changing. Here's a concrete example. Imagine we have a projectile, maybe a ball thrown upward, with its position described by this function. The position s of t equals negative 16t squared plus 64t plus 80, where position is measured in feet and time in seconds. Step 1. To find velocity, we take the first derivative of the position function. Velocity equals s prime of t, which is the derivative of our position function. Using the power rule, the derivative of negative 16t squared is negative 32t, the derivative of 64t is 64, and the derivative of the constant 80 is 0. So our velocity function is v of t equals negative 32t plus 64. Step 2. To find acceleration, we take the derivative of the velocity function. Acceleration equals v prime of t, which is the derivative of our velocity function. Taking the derivative of negative 32t plus 64, we get negative 32 for the t term and 0 for the constant. So our acceleration is simply negative 32 feet per second squared, a constant value. This constant acceleration of negative 32 feet per second squared represents gravity. The negative sign indicates the acceleration is downward, and the magnitude of 32 is approximately half the acceleration due to gravity, which makes sense for projectile motion problems. The key takeaway is that the second derivative gives us acceleration. It tells us how velocity changes over time. This connection between calculus and physics is fundamental to understanding motion, from projectiles to planetary orbits to the motion of particles. Now that we've covered the fundamentals of second derivatives, let's address the most common mistakes students make and share some valuable tips to help you master this concept. First, let's examine 3 critical mistakes that can derail your understanding of second derivatives. The first major mistake is confusing the first derivative with the second derivative. Remember, you must differentiate twice to get the second derivative. If f of x equals x cubed, then f prime is 3x squared, and f double prime is 6x. The second common mistake is misinterpreting concavity. When f double prime is positive, the function curves upward like a smile. When f double prime is negative, it curves downward like a frown. Don't confuse the sign of the second derivative with the visual direction of the curve. The third mistake involves calculation errors when applying the power rule. Remember, when differentiating 8x cubed, you get 24x squared, not 8x squared. Always double-check your arithmetic, especially with coefficients and exponents. Now let's discuss proven strategies to help you succeed with second derivatives. First tip, use visual aids. Sketch graphs to see concavity patterns, use graphing technology, and draw tangent lines to better understand how slopes change. Second tip, always check your work. Verify each step of differentiation, double-check signs and coefficients, and test your understanding with simple functions you already know. Third tip, practice strategically. Begin with simple polynomials before tackling complex functions. Practice identifying concavity from graphs and work through real-world applications to see the practical value. Let's quickly recap the key concepts. The second derivative measures how the first derivative changes. When it's positive, the function is concave up like a smile. When negative, it's concave down like a frown. Always remember to differentiate twice and check your work carefully. Remember, mastering second derivatives takes practice. The more you work with them, the more intuitive they become. Keep exploring examples and real-world applications. You've got this. Thanks for learning with us, and don't forget to practice what you've learned today.